Newton's third law is another one of those things that a lot of people can quote. Almost everybody can quote it, but don't necessarily understand it fully. Here you go. For every action, there is an equal and opposite reaction. Now, when Newton said action, back in the 1600s, the language was not well codified into the words we use today, and action and reaction have a very specific meaning. What he should have said, had the language been correct for the time, is for every force, there is an equal and opposite force. Forces come in pairs. If you think about it, you can't push something without it pushing back on you. When you contact something and then give it some effort, give it some oomph, it resists. It has to, right? If it has any mass at all, it must resist. Forces always come in pairs. And this is not always obvious. In some cases, it's pretty obvious. If you hit a ball with a bat, the bat slows down, which you know if you've ever really thought you were going to hit and you whiff instead, right? You swing really hard and you miss the ball and the bat just boom keeps going, right? But if you swing and you hit the ball, then the same force that causes the ball to speed up this way causes the bat to slow down the other way. For every action, there's an equal and opposite reaction. Means for every force, there is an equal and opposite force. One situation where this is less obvious, by a long shot, would be a car hitting a bug. Now, when a car hits a bug, most people would say, oh, well, the car hit the bug a lot harder than the bug hit the car, right? No, the car hit the bug at the exact same force. Same amount of force for the same amount of time. The huge difference was the acceleration. Remember, Newton's second law tells us acceleration is equal to force divided by mass. The car has millions of times more mass than the bug does. And so while they both experience the same force, the bug experiences millions of times more acceleration. A really extreme example of that would be when an apple falls from a tree. When the earth pulls down on the apple must pull with an equal and opposite force back up on the earth. Does that mean that the earth falls toward the apple? It does. But an apple has a mass of, what, a couple hundred grams? The earth has a mass of 10 to the 24 kilograms. So when you say A equals F over M, you are dividing by a number that is so big that the acceleration you get is super tiny. This is like the car hits a bug thing on steroids. It's a ridiculously huge thing, this planet that we're on. Although it's pretty small compared to, say, Jupiter, which is small compared to the sun, which is small compared to lots of other things. But regardless, this force being equal and opposite, the fact that the Earth falls towards an apple is weird, right? It's very weird. But it's not as weird as horses and carts. So one day a farmer wants to go to town, so he loads up all the vegetables and fruit and stuff he's ready to sell. He puts it in a cart, he attaches the cart to the horse, and he says, "Yeah, giddy up!" Unfortunately for this farmer, this is the late 1600s and the horse has read Newton. And horse turns and says, "Hey, I'm sorry, I can't pull this cart." Farmer says, "What are you talking about? You can't pull this cart." And the horse says, "Well, for every action there's an equal and opposite reaction. So if I pull on the cart forward, the cart pulls backward on me, we can't go anywhere, right?" And the farmer's like, "No, just pull harder on the cart." And the horse says, "No, no, no. For every action, there is an equal and opposite reaction. If I pull harder, then the cart pulls harder. And we can't move." Clearly, horses cannot pull carts. Newton says so. This is known as the horse-cart paradox, and it really puzzled people for a while. Obviously, horses can pull carts, so what gives? The key idea to understanding this is that action-reaction forces never act on the same object. When the car pushes on the bug pushes on the car. When the bat pushes on the ball pushes on the bat. When the earth pulls on the apple pulls on the earth. When the horse pulls on the cart pulls on the horse, right? Now, there's more than one pair of forces involved when horses pull carts. What does a horse do to pull forward? Same thing a car does. It pushes backward against the ground, in which case there is a reaction force that the ground pushes forward on it. The cart isn't pushing or pulling on the ground. It's got wheels. It's just rolling along, right? So the deal is you have two sets of forces. The horse is pulling forward on the cart, so the cart is pulling backward on the horse. But also, the horse is pushing backward on the ground, which means the ground is pushing forward on the horse. As long as the horse pushes harder on the ground than it pulls on the cart, it's going to go forward. Look at this diagram. The forces forward on the horse are greater than the forces backward, and so too with the cart. This, by the way, is exactly the reason why you cannot win tug of war by pulling harder on the rope than your opponent. It's literally impossible to pull harder on the rope than your opponent. You have to push harder on the ground than your opponent. Exact same idea, exact same reason. And it makes sense if you think about how to cheat at tug of war, right? If you make the ground slick, you put some ball bearings down, a little oil on the floor, whatever, they're going to have a much harder time. You're going to win because you can push on the ground harder. The horse-cart paradox and the tug-of-war I can't win by pulling harder paradox is really the same thing. So there you go. That's Newton's third law.